switch off a little bit from homological algebra per se, and let's start doing a little bit more category theory. So let's recall some things that we've done. Remember, if we have a category C and a category D, and we have a functor f in this direction, and we have a functor g in that direction, then we say that f was left adjoint to g if for every, well, if we have hom f a b is naturally isomorphic to hom, and functorially isomorphic to hom a g b. So this is in the category D, and this is in the category C. So let me give you a couple more definitions. So if I have a functor f, forget about the existence of an adjoint or not, but the functor f is, whenever you have a functor f, it gives rise to a map from hom AB in your original category C to hom in the category D, FA, FB, where if you have some f here, you just send it to f of f. And f is said, it's called faithful if this map is injective. Let me call this map phi. Phi is injective. It's called full if phi is surjective. And it's fully faithful if it's both. And fully faithful if phi is an isomorphism. Now, remember that if I have two functors, let's say I have f and h are two functors between these categories C's and D's, then a morphism between from f to h is a natural transformation. That is the data that for every, I think I'm using A, for every A in C, we have some alpha A that goes from FA to G of H A. So this is an element in hom D FA HA, making the following diagonal commute. So let's suppose that you have a morphism F from A to B. So here F is in hom C AB. Then FF is this, given is the same thing as phi of little f. HA HF goes to HP, and here by definition we have alpha B, and here's alpha A, and we make this diagram. We require this diagram to commute and to be natural, namely for any map. Well, that. Now, composition of two guys. Suppose you have a third functor from C to D, and we have a beta from H to K, then beta composed with alpha is well defined from F to K, and is given by beta composed with alpha of A is just by definition alpha of A. So this is a map from FA to HA, and then you compose with beta of HA. Beta of HA is a map from no, this is beta of A actually, which is a map from HA to KA. So this is a map from from FA to KA, which is what we want. And this satisfies all these axioms. So, so composition is well defined. So in particular, alpha is invertible. So here alpha is a map from F to G. If there exists a beta, which is from G to F, such that the composition of alpha and beta is isomorphic to the identity. Natural transformation from, well, beta goes from G to F, and then alpha goes, so this is from G to G. And the composition of beta with alpha is isomorphic to the identity from F to F. Okay, so now if I have a functor f, now we are in the situation where I have functors from C to D, F and G. I think I've used the right thing. Then I would say that F is an equivalence if you have isomorphisms from F composed to G to the identity functor in the category D, and from G composed with F to the identity functor in the category C. And the obvious statement is that if F is an equivalence, F is an equivalence with inverse G, if that happens. So if I have such an equivalence, then the first thing is to notice that is F is an equivalence then F is left adjoint to G, and G is, we have these two being adjoint, and F is fully fake. So let's check this thing. Let's check something stronger, perhaps. So you cannot have an equivalence if your functor is not fully fake. That's one of the first obstructions to a functor being an equivalence is whether or not it's full and whether or not it's fake. Okay. So, all right. So let's prove something a little bit stronger. So let's suppose that, remember the following situation, that if we have an adjunction like this, where F is left adjoint to G, and since I never remember the order of these natural transformations, let's do it. So we have this hom FA being naturally isomorphic to hom AGB. So let's choose B to be FA, this B to be of the form F of something, So if I put here that this is f of something, then here this is f of that something. And here we have the identity. Well, I can just now choose this b to be a. And I get a map from, so if I choose b to be equal to a, then I get a map from the identity of f of a. And I get an element here which goes to some element here, home, from a to g f a. And this is a natural transformation. So this is a natural transformation. So what I get is, if f is left adjoint to g, what I get is a map from the identity functor in the category C. Remember, these were functors from C to D to g of f in the category C. So that's a natural transformation that sends an element A, or an element A in the category C, it gives me this object here. And similarly, we get from the composition of f with g to the identity functor in the category T. We call this guy beta, perhaps. So this is my alpha. Okay, so all right, so the first observation I want to make is that let's suppose that f is fully faithful. Which is something extra. I'm just going to use the definition that I'm removing now. So, yeah, let's write it here. So let's suppose that f is fully faithful. So f is a left adjoint to g. And on top of that, it's this extra condition of f being fully faithful. So that means, again, that we have this map from home AB to home FA, FB, and that this is an isomorphism. Okay? Then I claim, and since I never remember, we're going to have to figure which one, that one of these two has to be an isomorphism. So I claim that alpha, and I reserve the right to remove alpha and change it for beta, is an isomorphism. Okay. So, okay. So how is that this diagram commutes? So how do we get this alpha? How do we get this alpha, or how do we get this this beta out of this construction? So for this, let me use a lemma that I'm not going to prove. That many of you have probably done it already, which is the following: is so this is a lemma, or perhaps before a lemma. Let me notice something. So let's suppose that you have f, which is a fully faithful functor. So we've already seen that if f is an equivalence, then f is fully faithful. How about the converse? So the converse is not true, but it's almost true. So if f is fully faithful, and for every element B, so f is a functor from C to D, and for every object in the category D, there exists some A is an object of C such that f of A is isomorphic to B. It's isomorphic to B. Then f is an equivalence. This is kind of true. It is true in the setting that we're always working on. I'm just going to mention this. I'm not going to dwell on this too much. So how do we prove that this is an equivalence? First of all, so this a functor of this form, it's called essentially surjective. So every object of the category D might not be exactly in the image of f, but it's isomorphic to an object that is in the image of f. And I'm not defining the image of a functor, it doesn't make much sense. But how do I make this theorem true? So let me tell you what the proof of this theorem is. So we need to construct the inverse. So we need to construct some g, which is going to be f inverse, that wants to be a functor from D to C. We're going to make a choice, and that choice is that whenever you give me B, choose any, this is in an object of D, choose any A that does this, given by this, and declare g of B to be A. And it's easy to check that you can extend this to an actual functor. And you need to use that if f is fully faithful. Suppose that you have some B prime and some map, some B prime, and you've chosen your A prime. And suppose that you have a map from B to B prime, let's say some G. Well, then what you have is some element, this G is an element from home in the category D of B prime. But B was given as is isomorphic to f of A, and B prime is isomorphic to f of A prime. This is how we chosen A and A prime. So this is isomorphic. When you conjugate by those isomorphisms, this is isomorphic to home f A prime. This is in the category D still, but f is fully faithful. So here what we used is essentially surjective, to choose A and A prime, and that's how we get this isomorphism. We conjugate by these two isomorphisms that we've chosen. But now since f is fully faithful, this thing here is isomorphic to home, now in the category C, A prime. And this is given by the inverse of the isomorphism that you get by the last isomorphism there in that board. Because f is fully faithful comes here. So now we started with G, which is an element here, and we've obtained by the composition of these two guys some element here that we define it to be G of G. Is the image of G under this composition of these isomorphisms. And it's easy to check that this is compatible with compositions. So the only part that is tricky in everything that I've said is this word here, and that requires some notion of choosing, and this will require, for example, that the class of objects on each category is an actual set, or at least one of them is an actual set, or that is equivalent to a set, and I don't want to get into that. So the question is, what does it mean to choose? And I know what does it mean to choose out of a set. I do not know what does it mean to choose out of a class. So if the categories are small, then choose means whatever you think it's choose. It's just pick an element of that set. Okay, so a functor that is fully faithful and is essentially surjective is an equivalence. So every fully faithful functor is an equivalence onto something. So as a corollary of this lemma, f is fully faithful. This implies that f is an equivalence from C into the category that I'm going to call f of C. And this is the category of objects B in D that are isomorphic to B in D such that B is isomorphic to f of A for some A. So exercise, check that that's an actual category. If you have two objects that are isomorphic to two elements that come from A or A prime, then you can define the set of morphisms, and there you're going to use that f is fully faithful. It's exactly the same chain of isomorphisms that I've chosen here, and that this is compatible with isomorphism, that the identities in such an object is there. So this is an actual category, and that this is an equivalence. Okay, so now I can actually state the lemma. Let C be a category. Let's pick an object in that category. And let's look at the category of functors from C up into set. So first of all, let's make that into a category. So this, so if I have two guys, F and G, which are functors from C up into set, then the set of morphisms is the natural transformation. So F into G is a natural transformation. Okay, so every object of C gives me an object in that category, which is the object H. So for every object in A, I can give you hom in the category C into A. No, actually, I want to do the contravariant one. So I'm going to do A dot. Oh, god damn it. Dyslexic. So that's a contravariant functor, so that's a functor from C up into sets. And let me call this functor H. So H is fully faithful. Again, my categories are all small. I don't want to deal with non-sets. So this is Yonela's lemma. Can be strengthened. I only need this. But the point is that, therefore, you can test an object. So in particular, any category C is equivalent to the category of representable functors. So what is a representable functor? Well, by this lemma, if you have a fully faithful functor, which is this functor h, then your category is equivalent to the image of that functor, which consists of all objects in your category D that are isomorphic to some f of A. So what's a representable functor? Such a thing. So a functor from C to A, a contravariant functor from C to sets, that is isomorphic to this functor, h of A, for some A. So this is a representable functor, and any category is equivalent to the category of representable functors in that category. Okay, so I want to claim this, that alpha is an isomorphism, and I'm going to use that lemma. And probably beta is going to end up being an isomorphism. Let's check that. Okay, so I've told you how to go from an adjunction. So if F is left adjoint to G, I told you how to get this natural transformation from the identity functor of C to this composition G with F. So how about the other way around? If I give you this guy, how do I prove that F is left adjoint to G? So if I've given you this alpha, I would want to get this isomorphism from Hom Fa B to Hom A GB. An alpha gives me a map from, for every A, it gives me a map from A into G, F, A. So, yeah, I think I always choose them in the wrong way. So I have a map from A to GFA. So I get a map from, so let's look at that, GFA to GB. Since I have this map, which is alpha of A, in that direction, and this functor is contravariant, I get a map in this direction. Which is given by this alpha. Now let's suppose that G is fully faithful, because of course I was going to get this wrong. So let's suppose that G is fully faithful. Then this is an isomorphism. This is if G is fully faithful. So now this isomorphism here is given by the composition of these two. And there we see immediately that if G is fully faithful, then this is an isomorphism and this is an isomorphism, therefore this is an isomorphism. So F is fully faithful, then beta is an isomorphism. And I just proven that if G is fully faithful, then alpha is an isomorphism. Okay? So the two proofs are exactly the same. It's just that if F is fully faithful, then I would have used a map from A to F, I'm sorry, from FGA to A, and then applied it here. Okay, so we see that if you have a functor that is left or right adjoint to another functor, and that functor is fully faithful, then you get that either this adjunction or this co-adjunction, one of them is an isomorphism. And that's a condition on this being an equivalence. If you're going to have an equivalence, then both of these guys have to be isomorphisms. All right, so that covers more or less the relation between being fully faithful and equivalences. And so I want to go into a little bit more of a geometric context, although it's not going to look like more than just the names. So first of all, we're going to be using that Yoneda lemma all the time. And I'm going to be using it in the linear setting. So let's remember, I'm going to choose K a field. It could be just a ring, but let's just pick it to be a field. And let's look at our categories to be linear. So my categories C's and D's are going to be K-linear. Remember, this in particular implied that the home spaces are K-vector spaces, and the compositions are K-linear, and adjunctions are going to be of linear functors and so forth. I'm never going to use any functor that is not linear. So in particular, when I look at the Yoneda lemma, now it's going to look like from C into hom, into functors from C up, vect. So this is K vect. And these functors are linear functors. And it sends an object A here into hom on C from dot A. And we use that our category is K-linear to say that this is a K-vector space. So everything is going to be K-linear from now on. And I would say that definition, a Serre functor in a category C is a K-linear equivalence. S from C to C is an equivalence such that for every A and B objects of your category C, then you have natural isomorphisms between hom AB and hom from B to S of A dual. And these are functorial in both A and B, and I'll let you check what does it mean to be functorial in both A and B. If you have a map from A to C, this functor is contravariant. You get a map from hom CB to hom AB. You get a map from hom S of A to hom S of C, but since you're taking duals, you also get a map in this direction. That's why we need these duals here, and we're going to require that this diagram commutes, and the same thing for a map from B to B prime, or from B to C. Okay? So it's clear what this functorial means in this setting. So that's what a Serre functor is in a category. And whenever you have such a Serre functor, then whenever you have such a Serre functor, then you get a linear pairing between hom B S A. I guess I could write this in several ways. I'm not really sure what's the right way of writing. Just a second. I guess I'm going to write it like this. Hom AB, at least this is general. Tensor hom BSA, and then we map it to the field K. If you give me some F here and some G here, then since this guy is isomorphic to the dual of that other one, then you use that isomorphism, so this F gives you an element in the dual of this vector space that you can evaluate at G. So that's this pairing that I'm going to write like this. Now, of course, it's going to be very hard to find these Serre functors unless these Hom spaces are finite dimensional. So it's very hard and probably impossible to find Serre functors. Existence of Serre functors is hard to prove. And in particular, it often requires finite dimensionality of these spaces. Of Hom spaces. And you see why, right? Because if you dualize this again, right, so this is again isomorphic by the existence of the Serre functor to Hom SA SB dual dual. And now since S was an equivalence, this space here is isomorphic to Hom AB. Okay? So you get an isomorphism from Hom AB to Hom Hom SA SB dual dual, which is Hom AB dual dual. And that's the rigidity condition of these Hom spaces being finite dimensional. So let's assume that the Hom spaces are finite dimensional. So the name Serre functor at least should be clear where it comes from. Remember that in complex geometry, if you have a projective variety or a compact variety, if you're looking at complex geometry, it's going to be compact variety. If you're looking at algebraic geometry, it's going to be a projective variety, a complete variety. And you look at the X groups of coherent sheaves, then those are finite dimensional, and you have the Serre functor is just take the dual of your sheaf, the linear dual of your sheaf, the old dual of your sheaf, and tensor it with the dualizing sheaf, which is the canonical bundle of the manifold. So that's an actual equivalence. So in the case of coherent sheaves on a variety X, where X is compact, then this functor S, this equivalence, is you give me a coherent sheaf and you send it to the dual tensor omega of X. And you need this compactness to get finite dimensionality of these Hom spaces to even start proving this kind of theorem. And it's hard to prove that this Serre duality is not a trivial theorem to prove. But it's there. And algebraically, it's just this what we need. We have an equivalence of categories that satisfies this condition for every pair of sheaves. I want to lift this to X groups, and that's a hard theorem. Okay, so at least we have one example where these Serre functors exist. And what's the nice thing about Serre functors? And this is a thing that is recurrent whenever you do geometry. Once you have Serre functors, any equivalence computes with Serre functors. And that's an interesting proposition. Let's suppose that you have a category C with its Serre functor S of C, and you have another category D with its Serre functor S of D. Let's suppose that the Homs are finite dimensionals. And let's suppose that you have an equivalence. Then, well, you can compose, you can apply S of C first, and then apply F Or you can apply f and then apply s of g, and these two guys are isomorphic as functors from C to D. Okay. I'm sure this is just completely abstract nonsense. I'm sure I'm going to mess up a few times until we prove it. But let's prove that. Okay, so I need to give you a map for every object of C, for every A in C. What I want to give you is a map from an element in home. Well, I need to give you a map from F of S of A to S of FA. That's what I want to give you, this alpha of A. Okay, so by Yonera's lemma, both of these guys are completely determined by the homes into those guys. So this is equivalent to giving you for every B, I would have a home from f of SA and I would have a home from B to S of FA. And to give you a morphism between these guys is the same thing as giving you a morphism of these functors, which is the same thing as giving you a morphism for these homes, which is compatible with with morphisms from B to B prime. Okay, but so let's do this now. How do I do this now? So we want to use the fact that both F and S are equivalences. I'm horrible to do these things in the board. Okay, so let's use this. It's the same thing as hom. By definition of Serre duality, this is the same thing as hom from FA to B dual. I'm using here that the spaces are finite dimensional, because I'm taking a dual of a dual. And now, how do I prove that this is the same? I need to use at some point that F is an equivalence to okay, I guess since F is an equivalence, it has an adjoint that realizes that equivalence. So let's play. Let's see if it follows from something like this. This is going to be this. That's just the fact that F is an equivalence. And now, since S is a Serre functor, this is the same thing as hom from A into F into S. Oops. Hom from A into F inverse of B dual. And now these two are the same, are isomorphic again because F is an equivalence. So we used here, here we used S in the category C is a serve functor. Here we used that S in the category D is a serve functor. Here we use that F is an equivalence, and here we use that F is an equivalence. Okay, so I've given you the map between, so the composition of all these isomorphisms gives you a map between the Hom spaces. This is clearly functorial in B, so this gives you a map between the objects by unit as level. So this in particular says that if a serve functor exists in such a category, it's unique up to unique isomorphisms, because if you give me any equivalence, it's going to send this serve functor to a conjugate. So serve functors are unique if they exist, which in principle, this is the definition I gave was very lax of what a serve functor is. It's essentially serve duality holds, whatever that guy is, and I'm proving that serve duality can only be of this form. Any other guy that, even though may looks different, as a functor is going to be isomorphic. So corollary for these categories, namely Hom spaces being finite dimensional, serve functors, if they exist, they are unique. Okay, so let me prove the last lemma, and today I guess we're also going to stop early. Oh no, I needed to continue a little bit, so otherwise we're never going to get there to prove anything interesting. So the following is interesting in a category with serve functor. Let's suppose that we have categories with serve functors now, and let's suppose that we have an adjunction. An adjunction between categories with serve functors. So I have a functor and I have its left adjoint. Okay, so I claim, and again I might do this wrong, so I claim that G is left adjoint to F. And now let's fix what are the corresponding serve functors on each one. So F is a functor from C to D. So this guy should be the serve functor on C, and this should be the serve functor on D. So this is saying that if you have an adjunction on a category where serve duality holds, then whenever you have a functor that admits a left adjoint, it also admits a right adjoint, and this is the right adjoint. In particular, well, remember that so that's the thing. So this says that whenever you have an adjunction, then you get for free a different adjunction, you get for free a different functor. And this is usually the definition for smooth manifolds, or for nice manifolds where you have this serve duality. You get to play with how to define. So if you look at a pair like pull back and push forwards of shifts, then you get an extra adjoint on the other side, which is the pull back upper shriek or the push forward lower shriek, which are not functors that are not trivial to define. In general. Okay, so let's prove that theorem. So if you have an adjoint for a functor in a category where you have serve duals, then that functor admits an adjoint on the other side, and it's essentially uniquely defined. because adjoints are uniquely defined, so that's the way that you compute the adjoint. Okay. So I think I did this correctly. So I've chosen F left adjoint to G, and I want to check that G is left adjoint to that thing there. So what I need to do is to pick hom. I need to prove that hom from G of B into S of F, oops, no, I'm sorry, into any A is isomorphic to hom from B into S of F of S of A. And this is for every B in D and A in C. I think today I've been consistent where my objects were. So this is in the category D, C, and this in the category D. So that's the adjunction that I want to prove, and I want to check it that it's natural, that I'm never checking it. Okay, so what can I say? So this guy here is hom of FSA B dual. That's the third duality in the category D. And now F, by definition, was left adjoint to G. So this is isomorphic to hom SA G B dual. And now this, by third duality, this is hom A S, oh, no, there's no S, G B dual dual. Oh, I need to shift this too. So third duality exchanges the order of these two guys and then removes that S. So this is GB A dual dual. And that's this. So the composition of all these isomorphisms is the adjunction that I want. Okay. So in particular, this gives you the typical example is, if you believe that third duality is given by what I told you before, that is non-trivial at all, let's suppose that you have a smooth map between smooth manifolds. This is a smooth map F between smooth manifolds. I'm going to correct this in a bit. What I'm going to tell you is not going to be exactly what it is, and it's just because. Let me state it, and then we'll fix that. Okay, so let's suppose. So we have an adjunction. We have seen that this guy is the left adjoint to this guy, I'm sorry, the other way around, that this guy is left adjoint to this guy. And these are functors from the category of, let's suppose these are proper manifolds. These are this smooth and proper map. Or if you wish, these two manifolds are compact. Compact manifolds. So that the push forward of a coherent sheaf is actually coherent on the other manifold. So if you look at coherent sheaves on X to coherent sheaves, I guess I'm doing this from Y to X. So we have the pullback and the push forward between these two guys. Yeah, by manifold I mean finite dimensional guys. Okay, so then this theorem is telling you how to compute that this guy has an adjoint on the other side, which is given by definition. This guy, well, not by definition, by that theorem, this guy is given by the Serre duality composed with this pullback, composed with the Serre duality 1 on x and 1 on y. So how do you compute this? If you give me a sheaf f, then this pullback lower shrink, again, this guy is a guy from x to y, and this functor here goes from y to x, so coherent shifts from y to x. So what you do for this guy is you first apply Serre duality on y, so you get this tensor omega y. Then you apply the pullback of this thing, and then you apply Serre duality on x, which is take the dual of this thing. This is again going to give you this f. This is going to give you tensor with the pullback. Oh, this is all pullback. Omega y dual. You take the pullback of this, and then you tensor with omega of x. So what this pullback upper shrink is, you pull back your sheaf and you tensor with the relative dualizing bundle, which is the dualizing bundle of x, tensor with the pullback of the dualizing bundle of y. Now, there's a caveat in something that I said, and it's that, and we're going to correct this, at least I'm going to state it, omega x is not what you think. To make all of these theorems true, this is not the top power of omega 1 of x, but it's rather that shifted by the dimension of x. And instead of looking at the category of coherent shifts on x, I need to talk about the category of complexes of coherent shifts, or complexes whose homologies are coherent shifts. So the dualizing sheaf is not just a sheaf on x, but it's a complex of sheaves on x, which is just this sheaf, but in degree minus the dimension of x. So we'll get to that in a second, and I'll start with that today. Well, not in a second. We'll get to that in a few lectures, but I'll start with that today. So to talk about that, we need to talk about triangulated categories, and I'm just going to give the definition today. Definition: a triangulated category see, it's going to be a linear category. So I'm always going to look at linear categories from now on over a field K. So it's just a linear category with a given equivalence. Which is going to be the translation from C to C. It's a linear equivalence. So this translation, I'm going to write it oftentimes if you give me an object in the category C. So you have this T of A, then I'm going to denote also A shifted by 1. But this is just a notation now to define T of A. So since T is an equivalence, then I have T inverse, and it makes sense to talk about A shifted by n for any integer n. And if you have a map from A to B, and T is an equivalence, so you get a map from, particular T is a functor, you get a map from A shifted by 1 to B shifted by 1. That is TF. I have F here, but then here I'm going to denote it F shifted by 1. This is just a matter of names. So a triangulated category is a piece of data which is a linear category, a linear equivalence, and a set of distinguished triangles What are distinguished triangles? This is just a couple of morphisms like this. So it's a morphism from A to B, a morphism from B to C, and a morphism from C to A shifted by 1. So a triangle is just a sequence of morphisms like this. No conditions are asked. Okay? So this is going to be a distinguished triangle. It's going to be, you give me 3 objects, and you give me a couple of morphisms. F, G, and H. So that's the data of that comprise a distinguished triangle. If you give me 2 distinguished triangles, I would say that I have a morphism of distinguished triangles if, suppose that you have another distinguished triangle, A prime, and you have some map B prime, and you have some C prime, and you have some A prime shifted by 1. Now, a morphism of this distinguished triangle is a map from A to A prime. Okay, alpha. No, I'm using different letters for this. J. A morphism from B to B prime, K. A morphism from C to C prime, L. And a morphism from A1 to A1 prime, but this cannot be arbitrary because I've already chosen this J. So this is going to be J shifted by 1. And I'm going to require that this diagram commutes. So such a thing, this collection of morphisms is going to be a map between distinguished triangles. And of course, I'm going to say that a map between distinguished triangles is, composition of maps of triangle is clearly well defined, and I'm going to declare an isomorphism to be an invertible map. Okay. So now, a triangulated, this was just to set up the definition. A triangulated category is a category of this data subject to the following axioms. And we'll discuss the axioms for a while before we get to the last axiom. So the first axiom is the axiom that the identity functor, the identity morphism, always gives rise to a distinguished triangle of this form. This is distinguished. So my category was linear, so this 0 object makes sense. This is the only morphism to the 0 object, and this is the only morphism from the 0 object. And I'm going to declare that this is a distinguished triangle. This has to be distinguished. I'm also going to say that any triangle that is isomorphic to a distinguished triangle is isomorphic. Is a distinguished triangle. Any triangle that is isomorphic to a distinguished triangle is distinguished. And finally, any morphism completes to a distinguished triangle. Extends to a distinguished triangle. Namely, if you give me a morphism from A to B, there exists some C and some morphism from B to C and some morphism from C to A1 in such a way that this is a distinguished triangle. Okay, so any morphism fits into a distinguished triangle. So let's look at this. This is going to be my first axiom. Let's look at this axiom. I'm going to give you 4 of those axioms, but let's understand this guy, because we've already seen that structure before. So in the category of chain complexes, we've seen exactly that structure. Actually, probably in the category of co-chain complexes in the way that I'm defining this. So we have seen, such structure in chains or co-chains over a ring R, over a K algebra, because I wanted my categories to be K linear, but that's kind of irrelevant now. Remember that if we have some F, which was a map from A to B, then we always, and these are co-chain complexes. So here A and B are co-chain complexes. So let's write them like this. These are co-chain complexes. Then we had the cone of F, and that cone of F satisfied that the cone of F satisfied this condition that you had a map from B to that cone of F. This was a complex that fit into an exact sequence of complexes where you had this A shifted by 1. I think it was shifted at -1 in the case of chain complexes with my notation. But if you just dualize every arrow, it's easy to see it. Okay, and I haven't required anywhere that these arrows be exact. There's no notion of exactness on a triangulate category. But in this case, this actually was an exact sequence of complexes. The category of complexes of cochain complexes is an abelian category. It's not a triangulated category, but at least this structure is there, it's underlying there. That I have this map from A to B, that I can continue to the cone. This composition actually is 0. This composition is also 0. This was exact. So we do have this structure. And this happens whenever we have any morphism. On the other hand, the cone of the identity was not 0. So I see something going on here. The cochain complexes allow me to have that axiom there when I actually use for C the cone of a morphism. It took us some time to prove that the cone of a morphism always fits here. And then if you give me one guy in particular, then you choose the identity, then you have the cone of the identity. And this fits there. So that's a triangle that is there. That's something that looks like a triangle that is there in cochain complexes. But if I wanted to have a triangulated category, then I needed to have this as a triangle. And I see a discrepancy here because this guy here is not 0. Remember that this guy as a chain complex was isomorphic to A plus A shifted by 1 with some differential. And these two maps here are just this inclusion and the projection. And this guy is certainly not 0. Whether this is an isomorphism, it's just equal, this is an isomorphism, and this is an isomorphism. So I already see something funky going on if I wanted to make the category of cochain complexes into a triangulated category. Because that first axiom seems hard to cope with the next axioms. So the second axiom, it's easier to check. It's easy to see that it's also going to hold for cochain complexes, is that if this guy and if and only if this is exact, if and only if, I'm sorry, I'm saying exact by distinguished. This is distinguished if and only if the triangle that starts with B to C to A shifted by 1, well, if I call this morphism F, I call this morphism G and this morphism H, then I have a map from C to A shifted by 1. This is H, this is G. And I have a map from A to B, which is F, Therefore, I have a map from A shifted by 1 to B shifted by 1, which is minus F shifted by 1. So this is distinguished. So that's an axiom. And notice that the cone actually satisfies this condition. In the sense that the cone was nice that it made this sequence exact, that you could extend it this way, but also you could extend it the other way around. You could look at the map from B to the cone of F to A shifted by 1 to B shifted by 1, and this also was there. Okay. So that's the second axiom of a triangulated category. The third axiom is what's going to start making things interesting. Is that if you have a map of triangles, A, B, C, A shifted by 1, and A prime, B prime, C prime, A prime shifted by 1. Again, a map of triangle, remember that if I had here F here, this was forced to be F shifted by 1. I have some G here. If I have something like this, making the diagram commute, so this is not yet a morphism of triangles. It's just a pair of triangles and maps like this. Then this exists, making this into a morphism of triangles. That guy might not be unique. And actually, whenever I say that there is a unique something, I think that they already corrected me many times. It's almost never true. But this one in particular, remember that this is not unique. Okay, so that's an axiom that says that this guy exists. Okay, so now we see that things are starting to get interesting. Also, once you have that this is a morphism of triangles, it's easy now that if F and G and F, well, if F and G are isomorphism, then this guy is also an isomorphism. G is an are isomorphisms, then H is also an isomorphism. And then this becomes an isomorphism of triangles. So now let's try to mix TR1 with TR3 for chain complexes. I've given you A to the identity of A, the cone of the identity, and A shifted by 1. And this I would want to make it into an exact triangle because this was what I've used to satisfy the second part of TR1 on cochain complexes. But then on the other hand, by the first part of cochain complexes, I needed to have this A, the identity of A, here, 0, and A shifted by 1 be a distinguished triangle. Now this is an isomorphism, this is an isomorphism, and this is an isomorphism. This is just the identity everywhere. So if I want to satisfy this TR3, I need to have an isomorphism this way. And this is not true. This complex here is not isomorphic to the 0 complex. Okay? I have a map between this guy and 0 and a unique map from 0 to this guy, and this is not an isomorphism. What it is true is that this is a quasi-isomorphism. So the cone of the identity is quasi-isomorphic to 0. It is exact. We've even shown that it was split exact. So the category of cochain complexes can never be a triangulated category because we are seeing, unless everything is 0, unless everything is exact. So cochain complexes over a field is, well, let's not get there. But you see that you can never satisfy TR1 and TR3 at the same time. Unless you make the cone of the identity be the same thing as 0. This needs to be an isomorphism. So what we're going to do is try to pass to a quotient where these two things actually become isomorphous. And then once we pass to that quotient, we lose the fact that my category was abelian. So it's no longer going to be an abelian category because I've identified these two things. But we see that we need to identify cones of identities, or by extension, any cone of any isomorphism, we need to identify it with 0. Okay, so that's my TR3. Another comment of TR3 is that let's look at the following thing. So let's suppose that we have some distinguished triangle. How am I going to do this? What did I want to say? 10 minutes. All right, so let's put names, F, G, and H, and let's look at this distinguished triangle, B to B to 0, to B shifted by 1. So now here we have a map, which is F. Here we have a map, which is F shifted by 1. Here we have a map, which is the identity. And if I go this way, I am applying F from A to B. And if I go this way, I am applying F from A to B. So this diagram commutes here. Okay. Now, here I see the map from B, this composition of B, C, H. And here I have B, and this composition here is 0. So now what I would want to say is why I would want that diagram to commute. How do I prove that? Oh, I guess I should have started with BR2. This thing here commutes if I just shift everything by 1. I'm going to get the 3 guys that commute here on the other side. Yeah, so let's see if I can do this quickly on this side, or if I need to use BR2. Okay, so perhaps I want to do something different. Let's do something different. I'm losing it. So what I want to prove is that B composed with G is equal to 0. So I want to prove that this composition here is the 0 map. If I had a map, if I had a way of making this into a map like this, then I would get, by composition, I would get 0, but this is probably not what I want. So let's do something else. Let's take, okay, so probably what I can do is take here C, here C, 0, and this is C shifted by 1. So here is F composed with G. Here is F composed with G shifted by 1. Here is G, which is the only thing that I can think of. So if I go this way, I get F composed with G. If I go this way, I get F composed with G and then the identity, which is F composed with G. So this diagram still commutes. Now, why? So this guy here is G. Oops, now I will want to check that that guy commutes. So that I show that there exists a map. So now it's true that if I prove that this thing here exists, then this is 0, and this, oh no. Yeah, this doesn't make any sense. Shit. This doesn't make any sense. Okay, so we want to have that C to be here, the identity. No, I'm not going to get to even state TR4. So let's check this. I had convinced myself that it was going to be with B and the identity on B. It has to be some game of this form. So let's see if I put here C and the identity of C. So that this way I get F composed with the identity. So let me try one more. Check that. 0, 0, then this is G, this is G. Okay, now at least this commutes. Okay, so let's see. This is distinguished by TR2. Probably I'm messing it up, and I don't remember needing to use TR2. But this is distinguished because C to C being the identity to 0 to C shifted by 1 is distinguished. Okay, so I'm just applying that TR2, and I get a distinguished triangle this way. Correct. So now from A to C shifted by 1, I just have F composed with G shifted by 1. And this is just the shift of the identity. So this is the identity shifted, and this is F composed with G shifted by -1. And this is just this diagram commutes. Now from here to here I have G, and then here to here I have the identity. So this is G, and this way is G. And from here to here I have 0, and from here to here I have 0. So this whole thing commutes. Now, since this whole thing commutes, then the composition of F with G here has to be 0 here, because this composition here is 0. The composition of this C shifted by 1 by C shifted by 1. Oh no, I'm screwing this up. I'm screwing this up. Let's see. We have 3 minutes. Let's figure this out. This is completely stupid. So I claim just TR1 plus TR3 imply that on a distinguished triangle, A shifted by 1, F, G, the composition of F with G is equal to 0. So what we need to do is we need to cook up another triangle where I have a map from A to C, which is the composition of F with G. And then in a different way, that is 0. So okay. I think the only thing that I can think of is C mapping to C by the identity, and here put F composed with G. Here put G. Here put 0. And here put F composed with G, G composed with F shifted by 1. So this and this commutes. Now what I would want, this is 0 and this is 0, so this guy commutes. And now this is 0, and I need to check why this composition here is 0. Oh, but then it doesn't matter. So, okay, so now we know that this diagram commutes for these 3 guys. So let's shift everything by 1. So if you have that 3 of these guys commute, then the next one has to commute. This is again TR3, because there was a unique map in this row, but then you can just shift using TR2. I don't remember needing to use TR2, but the thing is TR3, which is there, says that if this and this and this commute, then this guy exists and is unique. But now we have these 3, so just circle around with TR2 so that this guy here comes here. So that you're looking at that's correct. No, I'm looking at B into C, just exactly as TR2 says, into A shifted by 1, into B shifted by 1, and here I'm looking at C into 0, into C shifted by 1, into C shifted by 1. Now here is G, here is 0, here is G, so this diagram commutes. Here is F composed with G shifted by 1. Here is G shifted by 1. And now this guy commutes and this guy commutes. So this is the only one that we do not know if it exists and it commutes. But then since this guy commutes and this whole diagram commutes, this way you get 0, and this way, I need to check that one commutes now. Shit. Okay. And I'm already 1 minute late. So the question is, why does this diagram commute here? We've checked that this diagram commutes. This diagram commutes. The question is here, why this diagram commutes? Oh. That's irrelevant, actually. Yeah. Okay. Okay, I'll prove this next time. I can't see it now, unless someone can see it here. But the claim is that this composition here is 0 for free. Unless someone can see it. This kind of argument is stupid because it's not going to give me. So I need to put here the identity to C. What we need to do is to have this, and certainly here we want to see the identity to C, so that this composition is F composed with G, and then on the other side I want to get a 0. And yeah, the only way to see this that I can think of is putting identities like this and use the cone. So if we get here Z, and then here we're going to have something like this. But I do not know how to do this. Perhaps something like this. Don't know. I'll think about this for next time. I'll finish the definition next time on Wednesday.